All right, so we're going to try something new here, which is we're going to try two screens. And I think we're going to need to see this is my computer screen so that we can see the colors of the different graphs because they're all the symbols have different colors for them. And we're also going to need to see our page. Um, but just want to do this brief intro. We are going to do the results and discussion section. And I did look up what an acetate is. It has a C double bond O. It's like a carboxylic acid group, except it has carbons on both sides, so that I would know a little bit more about what we were talking about. But other than that, I'm going to be reading the results and discussion section for the first time while we go over this. That is something that I wanted to do to make it feel authentic. Like I haven't read this article, you haven't read this article. Um, and I've done that for all the other parts too, but just wanted to check in about that. Now let's go to the results and discussion section, which I think I have to on the other screen, which is looking at the page, and hopefully that'll shift the view. Now, let's see, we're on the results and discussion section and reading along. So this is going to be 3.1, ternary phase diagrams of prepared microemulsion systems. And the first sub one is changes in phase diagrams with the homology, so same yet system of the alkyl part CX with X equals 1 to 6 of alkyl acetates. So it's CX, meaning that it's going to be 1 to 6, but there's 2 carbons on the other side, which I now understand, used as oil component of water oil bridge 30 microemulsion systems. All right, I think we're making some progress here because good. Because I can, and hopefully you can, mostly understand what we're talking about. And it goes like this. So the oils, right, are going to be these acetates. And these oils are interesting. So my thought is, by the way, they're interesting because they're partially polar, because they have that O, that acetate, that's a ester group. All right, figure 2A and B show comparatively the Windsor 2 curves. So Windsor 2, remember, is Windsor 2 water microemulsion with water and oil droplets. And the Windsor 4 curves, that is the lower borders of Windsor 4 domains. All right, so lower border, right? So adding more includes more of that, where the amount of surfactant added is sufficient to create a single phase in the whole system for 6 ternary systems, 3-component systems, employing different acetate homologs. These curves essentially make up the ternary phase diagrams. In these diagrams, the mass fractions of the 3 components, water, ester, and surfactant, are plotted on the 3 sides of the Gibbs-Ruseboom equilateral triangle. I've seen a number of these phase diagrams before, but I didn't know that they were called Gibbs-Ruseboom, although I am a big fan of Gibbs free energy, and I imagine that's the same Gibbs. But good, maybe not. Between the bottom side of the triangle and the Windsor 2 curve, each system is inhomogeneous and does not constitute a microemulsion. All right, let's read that again. Between the bottom side of the triangle and the Windsor 2 curve, each system is inhomogeneous and does not constitute a microemulsion. Let's finish the paragraph and then we'll try and think what this means. Between its Windsor 2 and Windsor 4 curves, each ternary mixture forms a Windsor 2 system made of a clear, transparent water and oil microemulsion layer on top of the excess water layer. Above their corresponding Windsor 4 curve, the binodal curve, All right, well, I don't know what that means. I mean, binodal, two nodes, but all ternary systems become single-phase systems, that is, winds are 4 microemulsions. All right, so let's look at the curves in black and white. We've done this, these notes before. So we've got the Windsor 2-methyl acetate, ethyl, all the way down to hexyl, and the barriers are right here. First thing I can see is that the barriers are all in similar places. And as we go farther, and so, and then Windsor 4, okay, so hold on. So the bottom here is inhomogeneous below these lines. And the top here is Windsor 2 until you get to Windsor 4, and then Windsor 4 is up here. So let's see. These ones don't even go to the side, which is interesting to think about what that means. Let's see. So I'm going to switch systems here. I'm going to go over to share the actual journal article and zoom in here. Okay, so hopefully, yeah, there's a cursor here somewhere. So let's see. Green is here, and it looks like green goes up under these, and black is hexyl, green is methyl. I don't know which one we should choose. Propyl, maybe. Propyl just sort of stops right there, though. Well, let's look at the other one. And, excuse me. Methyl is green down here, Windsor 4, and it goes all the way down there. Hexyl, pink. All of them with a Windsor 2 stop around here, which is 25% water. Yep. And B, so with less water than that, there is no water. There is no water. There is no microemulsion. There is no Windsor 2. So if I think about what a Windsor 2 is, right, we'll stay here. A Windsor 2 is this one. It's got water. Oh, so there's not enough water to have a water below the microemulsion. That's what that means, I think. Um, Not enough. Okay, so, and the Windsor 4 takes over, and you can get some Windsor 4. So let's think about the methyl acetate. It's green. It's down here. It goes up, and then it stops. And so at all points, the green has to be higher here. Okay, so in this corner over here, close to the water corner, the mostly water, it looks like there's no Windsor 2 because there's not enough ester. Ester, increasing water, not enough water in this corner, or too much water. Not enough bridge, not enough oil, right? Oil is near 0 down. No, there's too much oil. I really got to think about these things. And then you get this middle region here with the green, and then there's too much water. So too much oil, too much water, a nice little mix in the middle here. And then again in this corner, too much oil. Oh, look, there's some little green ones down here. So it does go all the way to that side for the one component All right, I don't know what all this means, but let's go back and read. So I'm in the other screen, I'm flipping back here. Not that you can see it necessarily. Between the bottom side of the triangle and the Windsor 2 curve, so right down here, there is no microemulsion, it's inhomogeneous. And then between the green spots on the Windsor 2 and the green spots on the Windsor 4, that's where the Windsor 2 is. So right where my cursor is going to be Windsor 2. And then above that is where the Windsor 4 is. So this is going to be Windsor 4 all over here because there's some green spots that are hard to see down here. And maybe what I would do at this point actually is try and separate them. And I don't think they do that though. No, they always plot all of them together. So a useful tool, I think, would be to do the phase diagram of, say, just methyl acetate. I think that's actually something I've seen before. Um, and maybe we'll do that. Let's see. Uh, okay, well, anyway, so we have a sense of this. I'm going to go back to the other one. So let's see. And uh, all right, so the voice is now on the paper. Let's go back and read that. So using uh, Origin Pro software, let's show the actual part we're on. Using Origin Pro 8.5 software, the areas below each curve in the diagrams were computed, and the relative areas are reported as percent of the total triangle area in Table 1. Okay, good. So the table is so far. So methyl acetate, 12.97. Oh, that's under the Windsor 2, so no microemulsion. Microemulsion and Windsor 2 with water underneath it, and microemulsion with all of it in one phase. Yeah, are there trends? I mean, I see a trend here as it does generally decrease. So less Windsor 4, Windsor 2. I mean, it goes, it's low, it's high, it's low again. So butyl acetate has the highest Windsor 2. And over here, well, again, it'll probably tell us this, but and maybe there's less on this end and more, although we'll put question marks. All right, and now, okay, so let's see what it says about it. As can be seen from figure 2a in table 1, the lowest lying Windsor 2 curve corresponds to the system with MEAC, methyl acetate, C2 acetate, and the highest to the one with HEAC. Let's see, lowest. Yeah, that is a. So I can see what it's saying, but it is complicated. And so let's go back over here, and hopefully you can see. So the green one is the lowest, and the black one is on average the highest, although this no, the propyl one is highest here in this region. Okay. Well, right. So here we get into, I'm like, well, do I agree? Do I not? I can see what they're saying. So let's see. So MEAC is highest. All right. So let's go back to the other one. All right. I just underlined this. MEAC is the highest, and the one with the HEAC. Oh, sorry, lowest is MEAC, highest is HEAC, and I'm going to say okay, but I'm not super convinced, but maybe this is part of their argument. All right. This means that in general, the smallest amount of bridge 30 surfactant that needs to be titrated into the initial ester and water mixtures to reach a Windsor 2 system is minimal in the case of the shortest alkyl acetate and maximized when the longest homolog is used as the oil component. Okay, so what I get out of this is that more oil, more C's, more carbons, longer carbon chain or longer carbon tail, those are two words that we need to get used to and that I'm familiar with. Carbon chain and carbon tail, right? Because it's a carbon tail, and so the longer it is, the more tail-like it is. Okay, okay, I see what they're saying. I'm not 100% convinced, but I could imagine a trend. Since the formation of the clear water and oil Windsor 2 microemulsion implies miscibilization of the ester and water with the aid of the added surfactant, it is not surprising that the longer and more hydrophobic esters require higher amounts for non-ionic surfactant than the shorter ones. Okay, so I see their argument, and I can see, like, yes, I can, okay. So I can see what they're saying. I can see why they're saying it. Let's continue, because it's not a very convincing trend. All right, next page is the two graphs. Next page is the table. And the Windsor 2 microemulsions can serve as extraction systems for various analytes from aqueous media. For example, the removal of contaminants from wastewater or other contaminated water. And they give some examples. Therefore, a larger Windsor 2 domain area in the phase diagram would be desirable for such purposes. However, the data in the third column of table 1, 2, 3, should be judged only when taking into account the corresponding data in the other columns. It would be desirable that the enlargement of the Windsor 2 domain is the result of a lower Windsor 2 curve rather than an upper Windsor 4 curve marked by a reduction of the Windsor 4 domain area in table 1. The latter corresponding to higher consumption of the bridge 30 surfactant, which would imply a higher cost. Right, more surfactant, more costs. The oil and water, the water, I guess, is what you're treating. So the oil seems like you would want to, anyway, that's a cost too, I would think. Anyway, so I think, so this starts lower. All right, so we want low inhomogeneous region, high Windsor 2, at least for what they're talking about there. A larger Windsor 2 domain area in the phase diagram would be desirable for such purposes. Yes, so we want this to be lower, so we can get to the Windsor 2 first. We want this to be larger, so that's like one system. And then here, Windsor 4 microemulsion. So it's saying marked by reduction. Oh, so we want, hold on, let me read this again. It would be desirable that the enlargement of the Windsor 2 domain is the result of a lower Windsor 2 curve, lower Windsor 2 curve, rather than an upper Windsor 4 curve. So we want, right. So if this is big too. So we want lower and higher, or smaller and larger, or, I mean, right now we're looking for the largest, lowest, Windsor 2. I guess I should really start using Roman numerals for that to be consistent. All right, so clearly, although butyl acetate, yielded the largest Windsor 2 domain, already noted, this domain is delimited by high-lying Windsor 2 and Windsor 4 curves. Right. That is, requires high amounts of surfactant to form. The same is true for the other longer chain alkyl esters, pentyl and hexyl. ethyl acetate has fairly high-lying domain frontiers also, such that methyl acetate appears to yield the largest Windsor 2 domain, encompassed by the lowest lying Windsor 2 and Windsor 4 curves, followed by propyl acetate. However, a closer look at figure 2 reveals that due to the higher miscibility of, methyl acetate. So there's the miscibility. MEAC, miscibility. So we're interested in miscible systems with water, because you can't form a microemulsion or, right, that's what I'm getting, if they're miscible. Windsor 2 phases are not obtained at high water content, bottom right corner of the phase diagram. This region is of particular interest for water decontamination because the small amount of ester oil leads to small amounts of water oil Windsor 2 microemulsions that extract and concentrate the contaminants, leaving behind at equilibrium very large amounts of decontaminated water as desired. All right. So let's read that again. Well, let's read it to the end. Further, the high volatility of methyl acetate, boiling point 57 is pretty volatile, 57 Celsius, makes it an inconvenient ester for practical purposes. On the other hand, these inconveniences no longer exist in the case of propyl acetate, boiling point 102. That does make a big difference, which would thus be a more suitable ester from a practical standpoint. So they're suggesting propyl ester, which has 15% area under the curve before the Windsor 2, and only 10% in Windsor 2. And then, let's see, propyl is pink. Pink goes almost all the way over to the corner, and the color version of what's going on. Okay, so like that's 10% is not a very large region. It probably is large enough for them to hit. It's very close to water, 100%. Right. Whereas the methyl is not. The methyl only gets to about 75% or 0.75% water or 0.75 fraction water. Before there are no micelles, no microemulsion, and no separation, right? Because we're going to grab this microemulsion off of the water. Once the water and oil has equilibrated, the contaminants are in the oil droplets, the water droplets in oil, suck them off, separate them, find out how much contaminants in there. Do we want to go on, change the pace? That seems like a good place to stop for this video. And we'll do then more in the next one.